Hi all, welcome back to Capacitor and Dielectrics part 3. And today we're going to see energy stored in a capacitor. A charged capacitor stores electrical energy. The energy stored in a capacitor will be equal to the work done to charge it. A capacitor does not become charged instantly. It takes time. Initially, when the capacitor is uncharged, it requires no work to move the first bit of charge over. When a charge of positive dq is transferred from the negative plate to the positive plate, the charge on negative plate becomes negative q plus dq. And the charge on the positive plate increases to positive q plus dq. From the definition of potential difference as work done per unit charge, work done to increase the charge on the capacitor by dq is So this is the work needed to add a small amount of charge dq when a potential difference V is across the plate, where V equals to Q over C. Therefore, the work done to charge the capacitor to a charge Q is half Q squared over C. We have to carry out some mathematical process to justify the work done to charge the capacitor. Hence, the energy stored is half Cv square. We have to do some alteration to this formula. Have to eliminate Q by substitute V. When a capacitor is charged by a battery of constant EMF E is electromotive force of a battery and negligible internal resistance as shown in this figure. Charge is driven from the battery to the capacitor under constant potential difference E. Work done to charge the capacitor is equals to QE. Energy stored in the charged capacitor is equals to half QE. Energy dissipated as heat in the connecting wires is equals to QE minus half QE. Then you will get half QE. Let us try to attempt these A-level questions. Is about the capacitance of a variable capacitor may be adjusted between 1 times 10 to power of negative 10 farad and 5 times 10 to power of negative 10 farad. For section A, when the capacitance is 5 times 10 to power of negative 10 farad, the capacitor is charged by a battery of EMF 200 volt. What is the charge on the capacitor? From C equals to Q over V, Q equals to C times V, which is equals to 5 times 10 to power of negative 10 farad times 200. So charge on the capacitor is 1 times 10 to power of negative 7 coulomb. For the section B, the capacitor is disconnected from the battery and its capacitance change to 1 times 10 to power of negative 10 farad. For B Roman 1, what happens to the charge on the capacitor? For B Roman 2, what is the final potential difference across the capacitor? And finally, for B Roman 3, what is the work done against the electric field when the capacitance is changed? For B Roman 1, the charge on the capacitor is conserved. For B Roman 2, since the charge is conserved, so Q equals to C2 times V2, which is equals to C1 times V1. We're going to substitute all the possible values into the equation to get the final potential difference across the capacitor, which is equals to 1000 volt. Finally, for B Roman 3, work done against the electric field when the capacitance is changed equals to change in energy stored in capacitor. We're going to use this formula where half C2 V2 square minus half C1 V1 square. C2 is final capacitance, C1 is initial capacitance. We're going to substitute all the possible value into this equation to get the work done against the electric field when the capacitance is changed, which is equals to 4.0 times 10 to the power of negative 5 joule. Simple like a bubble without giving you any trouble. Let us try to attempt another A-level questions, which is an air capacitor consists of two metal plates, each of area A and separated by a distance of d. Ionization of air occurs when the electric field strength exceeds 3.0 times 10 to the power of 4 volt per centimeter. Find the maximum energy that can be stored in the capacitor in terms of A and D. This is the solution. If V maximum potential difference across the capacitor, then the maximum electric field strength is V over D, where 3.0 times 10 to the power of 4 volt per centimeter, we have to convert to volt per meter by times 10 to the power of 2. So the answer will be V equals to 3.0 times 10 to the power of 6 D. For the maximum energy that can be stored in the capacitor, we can use half CV square. Everyone knows that C equals to Q over V, which is equals to epsilon naught times A over D. Epsilon naught is the permittivity of free space, or we call it permittivity of vacuum if the space between the plates is a vacuum. And the value is 8.85 times 10 to the power of negative 12 farad per meter. Then we're going to substitute C as epsilon naught times A over D and V as 3.0 times 10 to the power of 6 D. Hence the maximum energy stored is 39.8 AD. Simple like a bubble without giving you any trouble. Thank you for watching this video. Thanks a lot and thank you to the Lord.